After a flood event, we are often left with a lot of questions, such as how high did the water get, what was the total discharge, and how does this event compare to past flows? To answer these questions, the USGS and its hydrographers employ a variety of techniques and methods to reconstruct the flow. The slope area method is a common approach. It allows hydrologists to recreate the peak water surface profile of a flood by using the high water marks left behind by the flood peak. Because the slope area computation relies on the high water marks left behind from a flow event, the data it produces is a single point showing stage and discharge at the peak of the flood. While this data is extremely valuable, it doesn't give us a complete picture of a flow event. The USGS has been working to develop a new method to measure stream flow throughout the entire event, providing more robust data during the rise and fall of floodwaters. This new method is the continuous slope area method. Its procedure is quite similar to the traditional slope area method and builds upon this foundation by utilizing 3 or more continuously recording pressure transducers within a stream reach. These sensors are quite small and can be installed at existing stream gauge locations. When these sensors are properly installed, they can more accurately document water surface profiles than surveys of high water marks. What sets this apart from the slope area method is that the sensors measure the water surface of the stream reach at 5-minute intervals, allowing for a complete computation of the flood hydrograph. This method provides a safer alternative to direct discharge measurements while providing discharge data at stream gauges that are inaccessible or have no provisions for making flood measurements. When considering the location of a CSA reach, there are a few guidelines to follow for best results. You want to choose a straight reach with a stable channel that doesn't undergo frequent scour or fill. Sensors are installed at 3 or more cross-sections that are similar in shape and area for a given discharge. These cross-sections should be located at breaks in the water surface slope, with a mild contraction in the reach being preferable to expansion. Lastly, there should be at least half a foot of fall between cross-sections. Aerial photographs can be very useful when deciding where to install a CSA reach. They can help you identify straighter sections of the channel and get an understanding of vegetation characteristics that may affect your data. If available, you can also look at previous slope area measurements, which will give you an idea of the cross-section characteristics. Additionally, you will want to reevaluate cross-section locations after flow events to verify that there's enough fall between the cross-sections and the cross-sectional areas are similar. The design of the installation will vary depending on channel composition and anticipated flow intensity. All installations are designed for low disturbance and survivability. This limits debris pileup and drawdown that can reduce the accuracy of the sensor readings. Here we have several examples of installations. One in a sand channel, a bedrock installation, and another in a cobble channel. Within the housing is the data logger, a non-vented pressure transducer that measures the water stage in 5-minute intervals. These transducers have the capacity to record 5-minute data for up to a year and have an accuracy of 0.03 of a foot. Since the stage sensors are non-vented, a barometer is needed on site to compensate for atmospheric pressure. 1 barometer at each site is sufficient. After a flow event, you will have to travel to the site to download the data from the sensors. To document that process, we've developed a field form with the necessary information you will need to record. For instance, you will want to document the condition of the sensor, whether it has been buried or has debris piled up around it, the condition of the cross-section, and any noticeable scour or fill. Additionally, you should compare the clock time reported by the sensor to the laptop time to check for any drift that could have occurred. To account for changes in channel shape, surveys are conducted upon installation and after significant flow events. You will need to survey the CSA pin elevations, cross-section geometry, high water marks, and gauge reference marks. A total station or RTK GPS unit can be used for these surveys. While in the field, you will also want to take photographs, noting the location and including something for scale, like someone holding a survey rod in the channel. This will help the evaluation of vegetation through time so that the channel roughness can be adjusted as it changes. The CSA method brings a safer and accurate alternative to the hydrographer's toolbox, allowing long-term streamflow data collection to occur in even the most remote locations. The stage data from the CSA gauges can also be used to calibrate 1- and 2-dimensional models. The This may be needed for low gradient channels where the slope area method may produce less accurate discharge data on the rise and fall of the hydrograph. However, the slope area method would still be used to compute peak discharge. The applications for this new method are promising, and by recording discharge data during the rise and fall of a flood event, we can now begin to apply that knowledge and improve current stage discharge ratings. We believe the CSA method can become a valuable tool to record hydrologic data, and we are excited to be able to share it with you.